So today I will talk about some recent research on war turbulence. Actually, Professor Marchioli may know that my research direction also includes the fluid flexible body interaction. uh, that's more close to his talk. But I'd like also to show some recent work on the war-bounded turbulence. That's also closely related to his topic, his previous talk. So here I'd like to first talk about the Gulf War turbulence and also to be more close to this multi-phase flow forum. So I also will show some ongoing work about the bubble-laden turbulence. First, some background. So in nature and engineering, it's a common phenomena for the Gulf War turbulence and the bubble-laden turbulence. And in these studies, we can see different phenomena and the mechanisms with the traditional single-phase flat wall turbulent boundary layer. And such study will also be beneficial for flow prediction, control, and optimization. Some typical example include the biofouling rough surface of shape and also the microbubble for shape drag reduction and so on. So here, so I'd like to separate in this kind of real problem. It may include both the rough war and the bubble-laden situations. But here I'd like to first separate this into two problems to study separately. So, so in war-bounded turbulence, so people are well known some classic theories and the typical characteristics like law of war and the near-war coherent structures. So it's well known that from the war, so along the war normal direction, so the velocity profile can be divided into the viscous sublayer, the buffer layer, log layer, and also it can also be classified into the inner layer and outer layer. And from the viscous sublayer, so we can also observe the typical coherent structures like the low speed streaks, the near-war streamwise vortices, the hairpin vortices, and outer layer very large scale motions from bottom to the outer layer. And recently, due to the development of the experimental technique and the numerical simulation, people can observe the interaction between the outer layer very large scale motion and the inner layer turbulence. But people also report different mechanisms, like the top-down mechanism proposed by Professor Malosik from Melbourne. So it shows some superposition effect and modulation effect. And also the bottom-up mechanism. One typical example is the formation of the packets of hairpin vortices. And also people also report some kind of supporting mechanism, interaction between the inner and the outer layers. So here we may ask that if we consider the Gulf War turbulence or bubble-laden turbulence, what's the behavior of the turbulence near the war? And we may check the outer layer similarity is still valid or not. The energy process, transfer process is modified or not. And can we propose some prediction model for this kind of more complicated situation? So my first so topic is for the Gulf War turbulence. So for actually, this is also a very traditional and older problem, and uh, peop people observe some kind of complex phenomena. So recently, so people observe that the strength of the outlier, very large scale motions, or secondary flows over the lava. So this is uh, so opposite to our intuition, because we may think that the lava have some kind of destruction on the near wall turbulence, but in some experiment numeric simulation, so such structures are strengthened. So then we may ask why. So the second interesting open question is the key parameter and the scaling of lava. So tradition, the very classic figure is a Nicholas diagram. It shows that the skin friction is a function of Reynolds number and the roughness height. And recently, scholars propose some kind of scaling for such Nicholas diagram. So it shows some the skin friction can be represented by a kind of single curve by proposing a scaling formulation. But here we may also consider for the roughness with different shapes. So usually it's in the transitional region. Then is there also some kind of universal scaling? And the third question is the outlier similarity. So here it's more diverse. So half people shows that the outlier, so the statistic collapse for different for the rough wall case and the smooth wall case, and but some other people show that in the outlier, the rough wall result deviate from the smooth wall case. So the outlier similarity is still valid or not is a very controversial issue so far. So we may also check this kind of problem by using our data. So here is several questions we want to answer. So by using our simulations. So this is the computational setup. So here we consider this kind of 3D waveform roughness. It's called the egg carton shape, and the computational the model and the boundary condition. So it's similar to the traditional channel flow, and here we use the coordinate transformation to transform the wavy mesh to the rectangular mesh. And also we use the pseudo-spectral method in the horizontal direction, and the finite difference method in the vertical direction, and the third order time splitting method for time advancement. And we consider two groups. Here K denotes the roughness height, and lambda is the wavelength, and S is the steepness. For group A, the K plus and the lambda plus are constant. They are scaled by the wall viscous unit. And for group B, K over delta is kept constant. And then as the Reynolds number increases, K plus and the lambda plus is increasing. So here shows some instantaneous field of two examples. One is I tau 540, and another is I tau 1000. So we can see the for I tau increase, for the same K plus, then the roughness in physical it's becomes smaller. So here we can see many near wall vertical structures, and they may also so form a kind of bundle of vertical structures. It's related to the outer layer very large scale motion. And we first check the mean velocity profile. For group A, the same K plus compared with the smooth case. So the Laufwall case where they have a downward shift of the mean velocity profile. But as the Reynolds number increase, they actually for the same K plus, the velocity profile is collapsed, but the log layer becomes longer. So we call this kind of downward shift. So this kind of downward shift is the roughness function. And for the group B, so K over delta is constant. Then as the Reynolds number increase, actually the K plus is increase. Then the mean velocity profile moves downward. And it means the roughness function is increasing. So then we plot the downward shift, the delta U plus, as a function of the K plus and the S is steepness. It's found that the different cases can be scaled by a kind of a single curve. If we simulate more cases, different K, and we can see they all collapse in this kind of single case. It means that the roughness function can be have a good scaling with this parameter. And moreover, we can plot the data from the reference. It seems that they all follow this scaling very well. And for the different references, they actually have different shape, like the cardan shape, the wavy shape, the pyramid shape, and the random shape. So by the K plus multiply S is a good indicator of the roughness function. And the people may be more concerned in the skin friction. So this is the classical Nicholas curve. So here is our cases. So we also find a good scaling for the skin friction and this scaling parameter. So that for the different cases, including with the reference data, all show very good scaling. So this can be used for the prediction of the skin friction of the roughness wall. And then we further consider the fluctuation. For the instantaneous quantity, it can be decomposed into the mean and the wave-induced fluctuation or phase fluctuation and also turbulent fluctuation. Here we mainly check the turbulent fluctuation. So this is the smooth case, and for the stringwise turbulent fluctuation, so we can see it's reduced. And for as Reynolds number increase, so this the peak is increased, but in the outer layer, it's collapsed with the smooth case. So here we say the outer layer similarity is hold. But as Reynolds number increase, so they show some deviation. For this is group A, but for group B, as Reynolds number increase, the K plus increase, then the outer peak, the peak is reducing and move outward. So this is the group for group B, and we can plot the peak value as a function of RE tau. So we can see it also shows this kind of log behavior. And we can plot this kind of peak value as a function for this scaling parameter. We can see all our data shows good scaling. And also include the reference data here. They all show this kind of good scaling behavior. And next, we check the outer layer similarity, as mentioned earlier. So as the Reynolds number increase, so it shows deviation from the smooth wall. It indicates the loss of the outer layer similarity. But this group B, as real number increase, actually K plus is increasing. But here it shows a better collapse. So this is also surprising. Why for the small K? So the outer layer similarity is more violated, but for larger K, it's a collapse well. So we check the spectrum. So for this is a smooth case, and this is the K equal K plus equal 10 case. We can see the outer layer peak is strengthened as compared with the smooth case. But for the larger K plus, so this is outer layer is weakened. So this is also kind of surprising why small K can have strengthening effect, but the larger K is a weakening effect. Then we check the instantaneous field of these two height, and we can see for the small K near the wall, the streak structure and the outer layer, it's the very large scale motions. But for the larger K plus, so the near wall streaks, low speed streaks is disrupted by the roughness. And as a result, the outer layer peak is not as strong as this one. And so this is a kind of instantaneous field. For the small K plus, so we can see it will form this kind of structure. But for larger K plus, it looks more complicated. So to understand more quantitatively, we check the transportation equation of the two-point velocity correlation. So this is the transport equation transformed into the scale space. So the production term, the pressure strain term, the turbulent transport term in interscale, and the physical transport term, and the dissipation term, wave-induced production term. So here we only show briefly some typical terms like production term and the physical transport term and the interscale transport term and the pressure term. Here K, small k and the larger K. So here we can see for the small K, so actually these terms are more strengthened as compared with the larger K case. So this also shows that the more intense turbulent transport for the small K. And we also analyze this phenomena, how the roughness affects the outer layer transportation. So we also derive the Kolmogorov equation, the generalized Kolmogorov equation in the curvilinear coordinate. So this is the flux in the scale space and the flux in the physical space. So then we can plot the energy transfer path from the wall. So this is the vertical position, and this is the scale, and from the wall, so it will go up, and so this is the attached plane. So this is the typical inverse energy cascade from the wall to the outer layer, and then to the small scale into the dissipation scale, this kind of process. And compare the rough wall case and the small roughness and the large roughness. So we can see to check these two parts, the small roughness obviously strengthening this kind of transport, but the larger scale weakens this kind of transport. So here we can see quantitatively how the roughness wall can affect the outer layer similarity. And okay, so this is I show some kind of schematic. To save time, I only briefly introduce. For smooth wall, the mean flow can transfer energy to the fluctuation due to the by the production term. And then it transfer to the other component by the pressure gradient pressure strengthen. But if there is a roughness, it will have additional wave-induced production and they have altered the transport term, interscale transport and the physical transport. For the small roughness, so it will enhance all these several terms. But for the large roughness, so it will weaken these several terms. So this is why the small roughness have a more significant effect on the outer layer flow. And we also recently we also check the random roughness. So it clustered in several different forms. Behind the clustering, so we can see the dense vertical structures. And for the regular one, so it will have no this kind of dense vertical structure. And we check the phase fluctuation. So it will show obviously the secondary flow. So, but for the regular one, so no this kind of secondary flow. Then and this is the mean flow. So we can also see the high momentum and the low momentum region. So it's also contrary to our intuition is that over the roughness region, it's a high momentum region, and the low over the smooth wall, it's the low momentum region. So if we look at the spectrum, so we can see this is the new secondary flow. But for the staggered regular one, so this is the outer layer very large scale motion. So due to the appeal of the secondary flow, so the original outer layer very large scale motion will be suppressed in some extent. So then we are also interested in how the energy transfer is altered by this kind of secondary flow. So we also check this transport equation. So this term is plotted here. So in the outer region, we can see the interscale. So to the small scale and the larger scale, this is the energy cascade and the inverse energy cascade. Near wall also flows to small scale and to outer scale, to larger scale. But if this is the rough wall case, then due to the appeal of the secondary flow, so it will change the energy transfer process. This is a very large scale motion peak will be much weakened. And the near wall also becomes much more different as compared with the smooth wall case. So then this is a kind of schematic. Originally, in the near wall region, there is the energy cascade region, the inverse energy cascade, and transferred to the outer region, the near wall region, due to the turbulent transport term. But here, due to the appeal of the secondary flow, so it will dominate the energy transfer between the secondary flow and its harmonic scale. So we'll have some kind of suppression effect on the original energy transfer. Okay, so I'd like to introduce the second topic. This is actually just an ongoing work. If there is a bubble in the turbulent flow, so here we mainly consider small bubble. So there are several key dimensionless parameters: the Stokes number, fluid number, and the Eötvös number. For the very small Stokes number, so the bubbles can be treated as a flow tracer. When the Stokes number increases, it will be trapped within the vortices. And the fluid number also, people found that for the small fluid number, the buoyancy force will cause significant slip velocity to lead to the crossing trajectory. And the slip velocity will also induce lift force to put the bubble to the downward side of the vortex. And if it's big, so the deformation will affect the lift force. But here we mainly consider the small bubbles represented by the Lagrangian model. And the bubbles will show some preferential concentration in water turbulence. It may be different with the solid particles. So in the upflow, so due to the lift force and the wall lift force, it will be concentrated in the near wall region, and also in the low speed streak region and the hairpin vortex region. So and in the downward flow, so it will show different behavior. And it will have also a modification on the turbulent flow, like the change the mixing density and the effective viscosity, and suppress the turbulent near wall coherent structures and so on. Another issue I'm concerning is the modeling. Based on the physical understanding, so it's also important to propose some kind of large eddy simulation model. So this is followed by the review of Professor Marchioli. So there are several classes of the SGS of the dispersed turbulence model, like the structural model and the stochastic model and some recent work. But most models so far are valid for homogeneous turbulence. So here we main concern the wall-bounded turbulence. It will have some very significant anisotropy. So then it will propose some challenge on the model I will show later. So we mainly consider the dynamics of bubble-laden turbulence and LES modeling. So first we will check the phenomena and the mechanism for the preferential concentration, and then to check to what extent the bubbles modify the flow field, and we also like to propose dispersed SGS model for the inertial-less bubbles. So this is the governing equation, and this is the equation for the bubble. So here we use a Lagrangian model for the bubble. So it includes the different force models like the gravity and the drag and the added mass and the pressure gradient, lift for wall lift, and the Bassett force. And this is the feedback force from bubble to the wall. So here we consider the two-way coupling simulation. The Reynolds number is low, 180, and the fluid number. So here we fix the volume fraction, and the diameter is changing. So the D plus is about 1, and okay, so this is set up. And at first, we'd like to check the different force models. We choose a set of force models for the drag lift and the wall lift. And also there are other options. So we compare. This is the base model. So we also check if we replace the drag model with the length model, but other models are keep unchanged. And this also if we change the lift force model, but keep the other force models unchanged, then we can see that for the different force models, basically this bubble velocity, they show quantitatively similar, qualitatively similar, so with some small difference. But for the density, so also they show similar behavior, but for certain force, this wall lift, different wall lift force models, they show significant different behavior. So because here there is no strict data for validation, so it's harder to say which force model is better than others. So here we basically consider these models are generally valid for the simulation. And another issue like to consider is the finite size effect. Theoretically, D should be much smaller than the Kolmogorov scale and the grid. But here it's about 1, and it's much smaller than the stringwise grid size, but may be larger than the normal grid size in the very near wall region. So we also test the two finite size correction reported in the literature. One is a function correction. It is taking into account the effect of local flow non-uniformity, just this term, into the velocity at the bubble position. And the second one is the undisturbed velocity correction. So it takes into account the effect of local flow perturbation. So by the feedback force. So so this is the result for the two different bubbles. But with the correction, we can see very slight difference can be observed by taking into account the finite size correction. Only within the viscous sublayer, so we can see a slight difference between the correction and the without correction. So this is the correction velocity. So for different bubble sizes shown here. Okay, so now we show some kind of statistical results. So this is the mean velocity for the small bubble. So it shows some difference, lower mean velocity. But for the increased bubble size, it shows almost the same results. This to compare with the bubble velocity and the flow velocity, we can see the bubble velocity is higher than the flow velocity. So it shows a very constant slip velocity across the channel. And the flow velocity at the bubble position will have some difference with the bubble velocity due to the preferential concentration behavior. Here is higher, but here is slightly lower than the bubble velocity. And for the reason, so this is the lift force and the wall lift force. We can see the lift force is negative near the wall, so it pushes the bubble toward the wall, and the wall lift force is positive. It will give the fast leave away from the wall. And as a result, for the different bubble size, so we can see that for the small bubble, near wall, the density is high. But as the diameter increase, so the near wall density is decreased significantly, and they show a kind of peak at the near wall position. So this also shows some kind of qualitative difference. And this is the instantaneous field. So for the very near the wall, for the larger size, so here the bubbles are more preferred to the high speed region. And for a little bit away from the wall, so it will be more concentrated to the low speed region. And corresponding to the near wall, so this is the negative velocity difference. And here, very near the wall, this is the positive velocity difference. And also, if we check the quadrant analysis very near the wall, so this is for the bubble velocity, it's concentrated into the fourth quadrant related to the sweep event of the near wall turbulence. And then above the peak, so this is the second quadrant related to the ejection event of the wall turbulence. And in between, so they will show some from Q4 to Q2, it will show the Q1 event. And to see more clearly, we also plot the normal force, the lift force plus the wall lift force. We can see above the peak region, so this is negative, and correspondingly, so it will have the positive normal velocity and the negative u velocity. So this correspond to the ejection event, and very near the wall, it's opposite, corresponding to the sweep event. And and then we may ask, near the wall, why it's much more increased? So this can be understood by looking at the relation, because the bubbles are concentrated in the high speed region. Then it will also correspond to the high velocity gradient, and also this will be related to the high lift force. Then so it will have a significant increased the velocity difference at this region. Then we check the velocity fluctuation. So we can also see the reduced velocity fluctuation for the small bubble. And okay, 5 minutes. Okay, yeah, I will finish soon. Yeah. So and if we compare the velocity fluctuation of the bubble and the velocity fluctuation at the bubble position, so we can see this is reduced due to the Q2 event, the preferential concentration. But near the wall, it's seeing that the span-wise velocity fluctuation is increased. So this is also related to the sweep, the event. And we check the energy transfer, or the mean kinetic energy transfer. So we can see that the main term is the balancing, is the transport, viscous transport, and the dissipation. And here we check the production term. So it's small compared with this term, but plotted here. So for the small bubble, so we can see it's have some kind of peak near the wall. Because for the small bubble, it's much more concentrated near the wall, so the density is high near the wall. So, but because the volume fraction is the same, then in the outer region, the bubble is reduced. Then it's the buoyancy force on the flow is actually reduced. As a whole effect, the work done on the mean flow is actually reduced for the small bubble. But for the larger bubble, so the near wall concentration is low, then for the whole field, it works like a pressure gradient force. It's almost uniform. And then for the small bubble, the skin friction of the turbulence is actually increased due to the reduced volume bulk velocity. But as bubble size increase, so it's almost constant, not changed. And then we check the turbulent kinetic energy. So as for the small bubble, so this is also reduced due to reduced flow velocity. But it's the work done the bubbles on the flow field is actually the BK. BK is here is very small. So, but for the small bubble, so it's a little bit higher. But compared with other terms, it's still here. For the resolved velocity, we also need to consider the SGS model, the subgrid model, for correct the resolved velocity to improve the bubble prediction for these different terms. So then the problem is how to build a model for this subgrid term. So the several method can found in the literature. One is the approximate deconvolution model. So this is use the resolved velocity to reconstruct the subgrid velocity. And the other is the stochastic model, using the Langevin equation to predict the subgrid velocity. So and we also have a test. So for the different models, they have similar density distribution and the mean velocity profile. But for the velocity fluctuation, so for the dashed line is the LES, solid line is the DNS. But for the LES with the subgrid model, so it will have more over predict compared with the DNS data. So, but for the V and the W, so it will be more close to the DNS data. So this means that all this model don't improve the anisotropic behavior. Because here here V is over predicted, but V and W are under predicted. So we'd like to propose a kind of anisotropic model to reduce this kind of anisotropy. So here we inspired by the classic LOTA model. So this is a return to isotropy model to formulated based on the anisotropy tensor here. So and the lesson and later the Hoas and the Pope propose some kind of Langevin model based, and then we could make some correction on the Langevin model to add a correction term. This is based on the anisotropy tensor to include this model, and combined with this term, then we have a correction of this term. Then, so to see the results, so then we can see the mean velocity not much different, but for the velocity fluctuation, we can see that this new model is more close to the DNS data. And for the V and the W, so it's increased, but for the U, it's decreased. This will have some improvement on the anisotropy problem of the wall turbulence. And then we check the velocity difference. So due to the preferential concentration, so these models are over predict the velocity. But here, because it will reduce this kind of anisotropy, so then it will be can be much improved compared with the DNS data. So it means that by using this model, these bubbles are more scattered, not focused on the high-speed region. But for the instantaneous field, it's not much clear. But for the statistical results, we can see this kind of effect. Okay, so I may also spend too much time. So I'd like to skip the summary, and thank you for your attention. And I'd like to take questions and comments from you. Thanks.
Yes, thank you very much, Wei-Xi Huang. Very nice talk, very nice presentation, extensive work on at least two topics. You also touched this last large area simulation attempt, which is also very interesting with bubbles. Now it's time for a little bit of discussion. So I'll take a few questions from people who would like to ask one. I'll break the ice with the first question Professor Yao raised on the chat. If you want to comment, I'll just read the question. How about the secondary flow found in the roughness wall case? So it was referred to your first part of the talk.
Yeah.
And commenting on secondary flows in that case.
Oh, wait a moment.
Yes.
Wei-Xi, because we know the second flow can be found in the band, can be found in the duct floor. No circular flow actually. Circular pipes can be found in the second floor. So for your case, you just found the second floor in the rough phase. So it's very interesting. So I'd like to know more detail of it. Yes.
So you are right. In a curved flow, so it's called the Ding's vortex or but here the secondary flow is induced by the non-uniformity of the surface. For example, here is the rough region. Here is a smooth region, and here is also rough region. So in this case, it will also cause the span-wise secondary flow. So this is also observed in many previous studies. So if we use different strips, for example, here is one surface, and here is another surface, and another surface, then there will be secondary flow in between. So this is similar to the problem you mentioned, but this is induced by the surface non-uniformity. So here also we cannot see the surface, but we can see the rows. So actually, one pair of rows roughly correspond to this region.
Do you get this working the mechanism of this secondary flow in the rough wall compared?
So the mechanism is actually the in the span-wise, it has the non-uniformity of the wall no-slip condition. So it will induce the secondary flow. So from the governing equation, actually we can also explain. So because the Reynolds stress transportation will be different due to the non-uniformity of the boundary.
Thank you. I get it.
So this is called the non-uniformity because it's different along the span-wise direction, but the structure is along the string-wise direction. So this is called secondary flow.
Thank you.
Thank you.
Any more questions on this?
I'll bet I may have a couple, if I may, but I ask in person.
Okay. So, welcome. Thanks.
One is actually a curiosity, since you are here on these slides on roughness. You have also simulated a random roughness.
Yes.
Did you consider only one case of random roughness or more cases?
Actually, here we consider 6 different cases.
These are all different.
So if you see, this is the clustering of the roughness elements. So this one here. So this different arrangement.
Okay. So the one on top.
But this is generated by artificially. So actually, if we made a computer program, we can produce infinity different styles of the roughness.
Exactly. So you say it's random, but maybe different random distributions might produce surprising results. That was something I was wondering. The other thing I wanted to ask, if I can have, well, maybe I ask one more. I have more than one, but I will ask one more, which is about the, I think it was on slide 50, where you show basically the effect of injecting the bubbles and, right? I think 50 or, so basically the bubbles are shown to induce a sort of constant slip velocity throughout. And that reminded me of something we also studied. So we did some years ago simulations of these small bubbles, so non-deformable, again, point moving micro bubbles. And we focused on the modulation of turbulence induced by these bubbles. And we thought, to sort of explain the effect of the bubbles as a sort of additional pressure gradient induced to the flow. So the unladen flow, you have a pressure gradient. We had the pressure gradient driving the flow. And when you include the bubbles, we had a vertical channel, so depending on the motion of the fluid, we could have an increase or a decrease of the Reynolds number that could be explained through these effects. So if you change suitably the pressure gradient, the mean pressure gradient that drives the flow to include the effect of the bubbles, you can rescale the shear stress at the wall. And that is basically rescaling the actual Reynolds number of the flow. Do you think this model, so it sort of rang a bell because that's exactly what we saw. And so I think maybe this is a good way of explaining the actual turbulence modulation.
You are right. That's actually what we observe from our results. The bubble modulation, it has a very slight effect on the turbulent field. So you can see it's maybe more clear from this kind of for the production term and dissipation term. So this is very similar to the single phase case. So the bubble work on the flow, turbulent fluctuation is actually several orders lower. So then as a result, the bubble as a whole is actually works like a pressure gradient by exerting the buoyancy force.
Right.
The only slight difference is very near the wall. Very near the wall, the density is very high for the very small bubble. Then, so it will have some kind of effect on the turbulence. So near the wall, very near the wall, it will have some effect on the turbulent field. So we can see the turbulent fluctuation has some kind reduced. But this is also related to, because for very small bubbles, the buoyancy effect is also reduced because it's much concentrated near the wall. Then in the outer part, so as the buoyancy force effect is reduced, then the mean flow velocity for the very small bubble case is also reduced. Then although the volume fraction are same, but for the buoyancy effect of the small bubbles are smaller than the other cases. So in this sense, so it's here for most cases we just can simply consider that the bubble effect on the flow field is to add a constant pressure gradient on the flow field. The turbulent field is also only very slightly modified by the bubbles. This is so much different with the high Stokes number solid particles.
The particles, that's very interesting. Very interesting. Thank you for the answer. There is one rather quick question also in the chat that remains to be answered. And it's for bubble-laden flow. Do you consider the bubble as a point for your tracking? Or I imagine.
So here we consider the bubble size is small. So the D plus is about 1. Then so it's treated as the Lagrangian point. So also when we submit papers, the referee also ask it's about 1. Then the finite size should be taken into account. So then we also check. And according to our result for this 1 D plus equal 1 case, the finite size effect can be neglected from according to our results, because it's maybe larger than the normal grid size, but much smaller than the stringwise grid size.
Excellent. Right. Thank you very much.
Yes, thank you.
If there is no other question, let me just have a very quick check. I see no.
Maybe one very quick. It's probably a yes or no answer. You mentioned you checked also the effect of the undisturbed velocity, so this correction. So for the bubbles, I understood it's not important. Have you tried also with some other, maybe heavy particles and stuff? Or would you say that it's something that we can neglect? Because I know people are working on two-way coupling of heavy particles. Some works are really stressing the importance. So probably, depending on the physical parameters of your particles, this correction may become important or not. It's good for bubbles, it's not.
So maybe, for bubbles, the effect is very slight, but for heavy particles, it may be taken into account. Should be taken into account.
Okay, that's also relevant, for particles. Well, with that, I think it's now time to close, to wrap up this very nice keynote meeting session. So let me thank the speakers, the keynote speakers once more. Cristian Marchioli, thank you very much once more, and Wei-Xi Huang, thank you very much also for sharing the slides. This is very valuable, so no, granted. We thank you very much. I think it was very interesting discussing turbulence with flexible fibers, with rough walls, with bubbles, so a lot of complex topic, very well addressed. So the research is very active in this field. So I'm glad to be part of the community. And with that, I conclude. I thank you once more very much, and see you next time. Thank you, Julia, also for organizing this event, and we'll be seeing next time, which is already set. So you'll receive all the typical information from Professor Yao. Thank you once more for attending, and see you next time.
Okay.
Thank you.
Bye-bye, everybody.
Bye-bye.
Thank you.
Good evening.